Hi, my name is Lilian and I am pleased to introduce you to the X-59 Lowering the Supersonic Boom team. My team members consisted of Biniam, Gebre, Aditya, Kumar, Alejandro, Zacarias, Anisha, Mulinti, Ansh, Dwivedi, Ezekiel, Pena, Isabella, Noreuil, Mahalia, Saavedra, Manav, Patel. Our mentor who guided us on the project was Rhonda McCarthy.
As the idea of bringing back supersonic aircraft back into the industry becomes more and more prominent, the X-59 project came up as a partnership between NASA and Lockheed Martin to specifically reduce the loud sonic boom noise that is regularly experienced with the supersonic aircraft to a soft thump sound.
To be able to study exactly how the X-59 is able to reduce the sonic boom to a thump, a list of tasks and goals were outlined within this project. These goals consisted of analyzing the X-59's specific design elements to study exactly why each of the components were designed how they were and placed where they were. Also, by using mathematics and simulation testing to be able to understand aerodynamic flow, what kinds of forces are acting upon the aircraft, like lift and drag, and finding the areas of low and high pressure. Additionally, by constructing an Arduino board and supplementing it with various components and code to quantify the sonic boom produced by the X-59.
A comprehensive methodology was designed to effectively dilute and present the following information. Our team was divided into various tasks. The first section details our team's in-depth research into the X-59's exceptional engineering. The design enables extreme noise reduction capabilities. The second section presents detailed calculations based on extensive open source data showcasing the forces acting upon the aircraft. The model testing segment covers our development of an accurate 3D model and testing the model for airflow simulations to test general airflow. Finally, the data collection and analysis section again uses open source data to demonstrate the X-59's ability to produce a subtle thump when breaking the sound barrier.
Ever since the Federal Aviation Administration prohibited supersonic flight in 1973, there have been several attempts to minimize the effects of sonic booms, primarily because of the benefits and of reduced travel time. So this design on screen has an elongated nose which spreads out the shock waves from the aircraft. So first the air will hit the tip of the nose, and it will propagate aerodynamically towards the tail of the aircraft. Also, because of the irregular elongated nose, a camera had to be placed on top of the aircraft to allow the pilot to be able to see the outside. The engine was also positioned at the top of the aircraft so that most of the shock waves would be deflected towards the sky rather than the ground. Additionally, the inlet manages the airflow into the engine to prevent low energy boundary layer from being ingested and ensuring smooth airflow despite the top mounted engine position. And finally, the aircraft incorporates a swept back wing to be able to reduce drag. All of this makes the X-59 aircraft able to reduce the sound of a sonic boom to a thump.
In order to test the airflow of the X-59, we decided to try using a wind tunnel simulator. Initially, we started by downloading the X-59 model from NASA's website. However, it came with a stand that would skew the results. So, we imported it into CAD and 3D modeling software to remove it. We started with Onshape. However, the model had some faulty surfaces. We attempted to repair the faulty surfaces in Fusion 360 and Onshape. We managed to solve them in Fusion 360. However, the 3D model wouldn't work in our wind simulator, OpenVSP. So, we tried to convert the model into a usable model for OpenVSP. When OpenVSP didn't work, we switched to Blender.
When we switched to Blender, we started by removing the stand vertices. This gave us a successful STL that we would be able to use to simulate a wind tunnel. We tried finding a program that would help us create the wind tunnel, and we went through loads. We went through OpenVSP, OpenFlow, and Flow3D, but in the end, we ended up deciding to use Blender because all of the other softwares either would have taken too long to set up or they would have used too much processing power than we have available. So So when we went into Blender, we attempted to simulate a wind tunnel. But when we did that, the resolution was too high and it was trying to simulate realistic lighting and the visual smoke was not working. So we redid the process in Blender and we got a wind tunnel working at a resolution where you can tell what the smoke is doing pretty accurately and there's no realistic
Due
light.
to the limited results from the 3D simulation software used pertaining to lift and drag data, the team used the modern lift and drag equation to simulate the possible lift measurements based on standard data values. As NASA doesn't release the specific coefficient of lift of the X-59, the team used a similar aircraft called the C-25D, which includes the same characteristics as the X-59, such as the long nose and engine placement being at the top and the swept-back wing. Additionally, the team used the ICAO standard measurements for air density at 55,000 feet to use as an accurate measurement, as there isn't currently data released by NASA regarding air density of where the X-59 would be flying in. After performing the calculations based on the X-59's velocity and cruising altitude, the team formulated the lift of the X-59 to be 13,725 pounds of force and the drag force being 8,286 pounds of force. To be able to assess which phase of flight the X-59 could be in, the team referenced the coefficient of lift versus alpha graph. The corresponding angles of attack as a result of the low coefficient of lift measurements would be a negative angle of attack. Since, based on the data, the weight of the X-59 is greater than the force of lift, also the force of thrust being greater than the force of drag, and the angle of attack being negative, the team hypothesized that the X-59 could be inside
The images to the right show the pressure distribution at different sections of the X-59 in supersonic flight. The first image displays a colored palette of pressure when the X-59 travels at supersonic speeds. These colors are valued to show higher pressure at red and lower pressure at blue. As you can see, the cone shape is formed as the aircraft is moving at supersonic speeds and is moving faster than the sound waves. Additionally, you can see higher amounts of pressure measured in pascals at the nose of the aircraft and the rear where the boom dissipates. The data shows the high pressure shock waves at the nose followed by low expansion waves at some places such as the inlet located at the rear of the plane, which experiences spillage resulting in higher pressure in the area indicated. The second graph shows a monochromatic distribution of the surface pressure in a simulate when the X-59 travels at supersonic speeds. Just as before, the cone shape is formed as the aircraft is moving at Mach 1+. The differences in pressure can be explained based on the position in which shockwave and expansion
We
occur.
needed to devise a testing plan utilizing the Arduinos for microphone experimentation. Several people in our team worked on coding the Arduinos and Cduino, and we successfully lit an LED light that reacts to sound waves. We then calibrated different frequencies of instruments to ensure the microphones functioned correctly. After the calibrations were successful, we simulated flight data by surrounding a plastic box with bubble wrap. We inserted different microphones into the box and played the sonic boom on a Bluetooth speaker to collect the data for analysis.
During the initial phase of our Arduino project, we connected an Arduino Uno to a breadboard and implemented LED lights to confirm the functionality of our microphone. We tested various microphones, both built-in and external, and explored their respective qualities. Next, we added an SD card reader to store data on an SD card. We collected specific data on the sound, amplitude, and frequency of each microphone. Our observations revealed that some microphones were more sensitive than others. This detailed data allowed us to understand the strengths and limitations of each microphone. The more sensitive microphones showed promise for applications requiring the detection of subtle audios, while others might be better suited for environments with higher noise levels. Additionally, we experimented with various configurations and placements of the microphones to optimize their performance. For instance, we tested different angles and distances from the sound source to determine the optimal setup for maximum sensitivity and accuracy. This iterative process of testing and refining our setup ensured that we achieved the best possible results for our project.
We had a couple people working on already assembled microphones while I tackled building one completely from scratch. I used a microphone with 2 strings and worked with attaching all the components. For future scientists, I would not recommend this microphone as it was very involved and there were some code malfunctions with it.
This code is designed to use the Arduino to detect sound and indicate the detection through an LED. Two key components are connected to the Arduino, a sound sensor on digital pin 2 and an LED on digital pin 3. At the top of the code, we have these two components declared and initialized. In the setup function, the pin mode function configures the sound sensor pin as an input, meaning it will read data from the sensor, and the LED pin as an output, meaning it will control the LED. The loop functions runs continuously, constantly checking the status of the sound sensor using the digital read function. If the sound sensor detects a sound indicated by a high signal or 1, the code turns on the LED by setting the LED pin to high using the digital write function. If no sound is detected, indicated by a low signal or 0, the code turns off the LED by setting the LED pin to low. Here's a demo of this code.
This is the code to make the SD card reader function. The first arrow is pointing to the code that initializes the SD card, gets it started, and able to be written to. The second arrow is pointing to the code that creates and opens the file, as well as adds the titles of the two columns that will be frequency and amplitude. The third arrow is pointing to the code that converts the data onto the CSV file, and the fourth arrow is pointing to the code that uses the digital write command to turn the LED on and
In
off.
Arduino Phase 2, we worked on a sealed container with bubble wrap insulation. We used a sealed container so no sound waves would escape. We also insulated the container with bubble wrap so no echoes would affect our data. In the box, we had our speaker and Arduinos that would emit and pick up the sounds. With our variables, we had independent variables, a microphones, and frequency and amplitude provided. Our dependent variables was frequency, amplitude, return. Our controls were a sealed container, bubble wrap insulation, Arduino board, and the distance between the speaker and the microphone, which came out to 52.5 centimeters. Regarding the process, first we made sure the speaker worked, so we tested frequencies from 200 Hz down to 100 Hz. From there, we were able to get a consistent data, so we knew the speaker worked. From there, we tested 20 and 40 Hz on the microphones.
When performing the calibration readings at 20 Hz and 40 Hz, there hadn't been consistent and valid results with the microphone. These issues could be attributed to a multitude of different reasons, such as having a poor speaker that couldn't have emitted a great sound, or a frequency checker that wasn't able to quantify the low frequency sounds accurately, or not getting the correct sampling rate for the Arduino board. So, the team simulated what the frequency versus amplitude graph would look like to the right. The team would expect there to be peaks in amplitude at 20 Hz and 40 Hz, as those were the frequency sounds that was used to calibrate the instrument. The reason for picking to calibrate the instrument at 20 Hz and 40 Hz is because most of the energy that is produced in sonic booms are concentrated at a frequency range of 0.1 Hz to 100 Hz.
From the Arduino testing, we wanted to get the pressure versus time and amplitude versus frequency graphs for the X59. The human ear can hear at a frequency range of 20 to 20,000 Hz, with it being the most sensitive to frequencies in the range of 1,000 to 3,000 Hz. Anything below around 50 Hz is very difficult for the ear to detect. Dr. Kevin Crosby provided us with 10 simulated flight overpasses of the X59, and they are simulated with the standard IKO atmospheric model with the X59 in the cruising stage. The amplitude versus frequency graphs for the 10 simulated flight overpasses shows that most of the sound produced at frequencies above 50 Hz, which are very easy for the ear to detect, have very low amplitude, and are thus imperceptible. The amplitude is high for frequencies below 50 Hz, which are very hard to detect. What all this means is that the X59 has a very low sound profile for the human ear. The pressure versus time graph for the 10 simulated flight overpasses also shows that the end pressure wave graph has more rounded peaks than those for other supersonic aircraft, which shows that the sonic boom is softened and the waves are more spread out to reduce extreme pressure
We
and noise.
compared the prices of the microphones tested on the different Arduino and Arduinos to their data collected. This red high sensitivity microphone is attached to the Arduino, and it is the most expensive of the microphones tested. This expensive microphone has a tendency to have a great digital but almost useless analog, and its data proved this by not providing significantly finer data than any of the other microphones tested. But it also required a lot of sound to light the LED, so we decided this microphone is not worth the price. We also tested the cylindrical electret condenser microphone on an Arduino. It's simple, reliable, and inexpensive microphone with just 2 wires. We were unfortunately not successful in the timing and coding of this microphone. We have tested several codes, but we could not just make it work. The best microphone we tested on the Arduinos was the blue high sensitivity sound microphone, which is deemed to be really reliable. It picked up our voices as we were speaking in the room, meaning it was extremely sensitive, making it a fantastic microphone to measure the sonic boom. It isn't as expensive as the red high sensitivity microphone, and for its data, we concluded the blue high sensitivity sound microphone would be worth the price.